Okay guys, so today we are going to start a new topic which is called combined stresses. Now, as the name suggests, it is a combination. It's combined stresses, so it is combination of different stresses. So in other words, you have such sort of scenarios where you have got different loads which produces different stresses, and you are asked to find resultant stress. Okay, or it can be a summation of all the stresses. So how do we sum up our stresses? We take a section and we see that how many different types of loads are there and what sort of loads are contributing to the stresses imposed on that particular section. So you will see what I mean. Like for example, imagine we have a simply supported beam which is subjected to sub-loading. So it's a vertical load applied on a longitudinal structure. So clearly this will cause flexure stresses. Yeah, because it's a vertical load, it's perpendicular to the longitudinal axis of the beam. So it will cause shears and it will cause flexure stresses. Now you have another, you have got the same beam on which another set of load which is in another direction, that is a tension applied. Okay, so this load will cause flexure stresses, this will cause tension stresses. So all the loads, in other words, which are in, let me call it case A. Okay, so this is one beam which is subjected to these two combination of loads. But we get combined stresses when the nature of the load is different or the nature of the stresses produced by the load is different. What do I mean? Like you can have thousands of vertical loads over here, but all of them, they are causing flexure stresses. So this is one type of stress which is produced by multitude of loads. But however, this is completely another type of load which is called tension force. Okay, and this is called tensile stresses. This is causing tensile stresses. So that is another different type of stresses. So you can have hundreds of loads which are axially applied. Can be tension, can be compression, but all of them they cause tensile. They call axial stresses. Okay, that can be tensile or compression. So they are different. Okay, the nature of the stress is different. So what we do is we take these stresses which have got different nature, study or examine one cross section and see that what sort of stresses, resultant stresses are produced on that cross section. So first of all, the stresses can be flexure, can be axial, can be torsion, can be different types of stresses. But in order to add them, you must make sure that all these different types of external loads which are applied, they produce internal stresses which you are able to add. That means that they should all be in one direction. I can't have a load, a stress in this direction. Okay, imagine I've got a stress in this direction and I've got another stress in this direction and I start adding that. That doesn't make sense. Okay, I must have, so these stresses, actually you can decompose the stress into loads, isn't it? You can have set of loads which are applied over here on this cross section. These stresses can be decomposed into any set of loads. So imagine one stress gives you this sort of distribution, okay, or the one type of external load gives you this sort of distribution or internal stresses, and another one should give you something like this or something like this. Or I mean something like this again, which can be added up. My point is that if you are checking a type of stress on a particular cross section, you should be able to add them up. But due to the fact that they have got forces in the same direction, you can always sum up forces which are in the same direction. For example, all the forces which are in the x direction, you can sum them up. All the forces in the y direction, you can sum them up. But you can't sum up x with y. Okay, so the combined stresses, we have to make sure that whatever reference cross section we are looking at, we check different type of stresses which are applied on that cross section, and if they are in the same direction, then we sum them up. Okay, so let us test that. Over here we have got a beam subjected to vertical load. Over here, then and in addition to that, we have a tensile force which is developing over here. So this will produce compression in the top fiber. Imagine my reference axis is AB. Okay, so this I am trying to find out stresses in AB. Okay, in AB. AB is just one reference cross section which is of interest to me. So I am trying to find out my stress in AB. So first of all, I will check how much flexure stress is running into my AB. So the way to do that is the flexure stress is My or I, isn't it? So I will find out my My or I in this cross section. So imagine my My or I comes out to be this is compression . So this is compression at the top and tension at the bottom. So that is my flexure stress which is running into this beam or at this cross section. Now, in addition to that, I have a tensile stress. So tensile stress is on this is our tensile stress. So see, when I add these two stresses need to be added. Why? Because they are in this direction. They are in the horizontal direction, so I can clearly add them up. So you see, this portion which is above the neutral axis, that cancel out some effect of this compression because they both are in negative direction. Okay, and below the neutral axis, I have tension and plus this thing which is already tension due to flexure. They both add into the effect. So imagine I can get something . So imagine what has happened is that the magnitude of this one has increased and the magnitude of this one has decreased. So, and the neutral axis will be shifted. Yesterday we discussed that the way to shift your neutral axis is via the applied load, isn't it? in the unsymmetrical bending, I told you that if you change the applied load, okay, you will change or shift your neutral axis. So let me make it a bit more clearer for you guys. So what I'm saying is, so you see, neutral axis has shifted, yeah, and my tension has increased and my compression has reduced. So this is called combined stresses. I have added these two stresses at a particular cross section, and the load was in the same direction, stress was in the same direction. Okay, stress is force by A, so you can call stress or you can call it as a force. You will follow the direction of the force. So they both are in the same direction, and what happens is that your neutral axis has been shifted, and you get another stress force. Okay, this is called combined stresses. That's normally happens in different structures where you have got different nature of loads and external loads applied. Okay, so in reality, as I told you, that this structure is actually subjected to load in this direction and load in that direction. So we have got two different types of loads. Now that we can solve a very quick example based on that. Okay, so we have got this bracket which is subject to 25 kilonewton load, and we are asked to find out the maximum stress at a particular cross section. So remember that it's or please notice, I should say, that it's a cantilever. So cantilever has got maximum stress at the root. Okay, so it is at the support where we will have maximum stress. Okay, and so what we can do is, now based on this example which we have done, we can just write our general stress equation as stress is equal to P by A plus minus M y over I. That is our general stress equation. We have got P by A, stress due to axial forces, and plus M y over I, which is the flexural stresses. Okay, so in here also, this 25 kilonewton can be decomposed into 15 kilonewton and 20 kilonewton. Now, you have to transfer this force to this point. So, in other words, you have a couple. Okay, so this couple So in other words, you have a 15 kilonewton in this direction, you have a 20 kilonewton in this direction. I can add and subtract a 20 kilonewton load. So this 20 kilonewton will make a couple, and we will have another tensile force. So in other words, what I am saying is that on the cross section AB, I would have 15 times 450. What is 15 times 450?
6750.
6750. So amplitude to Newton meter or 6.75 Newton meter. In addition to that, so this is due to the cantilever 15 kilonewton load. Then we have a couple. This couple is 20 and 20. So this is a couple which is in this direction. I'll show it in a different color. So 20 into 20 into 150.
3,000.
Sorry?
3,000.
This is the couple, which is 20 and 20 and into 150. And then you have, so this moment plus this, plus you have a tension force which is 20 kilonewton. So what we have done is we have three different forces. One is the 15 kilonewton, so that goes straight. Okay, imagining that this is a rigid body, so that goes straight. So we have 15 kilonewton, which will cause a moment. Okay, that moment is 15 times 450, which I have shown over here. Then, so this is the applied load, it's not the resisting load. Then we have this couple, and okay, because we have got 20 kilonewton, we have got this 20 kilonewton, that 20 kilonewton, we can say that at this point we can add and subtract our 20 kilonewton, and these two 20 kilonewton makes a couple, and that couple is causing an opposite moment, which is 3000 Newton meter. And in addition to that, we have got 20 kilonewton, which is the tension force. Okay, so now in this equation we have area. So area we already know, area is equal to we have got moment of inertia, which we dh by 12. So in this formula we know A, we know I. Okay, y would be the extreme end. So y is equal to 150 by 2, that is 75 millimeter. Moments. This moments will be, this moment would be this minus this, whichever is bigger. Okay, so you see 3000 minus 6750. Okay, 6750 is bigger, so just subtract 6750 minus 3000, and that is your moment. So moment you would know and we have applied load P, and that P is 20 kilonewton. So P we have 20 kilonewton. Now, please notice that if you put in this equation P as in kilonewton, you have to convert this also into kilonewton. Okay, it should be like with the like. So, or either you should use 20,000 into. So, for the maximum stress, these two must add up. If we make one positive and one negative, what will happen? They will, that will be reduced. That will be reduced stress. Okay. So, for example, because we have this one, this moment, which is 6750, that is bigger. So, this moment is bigger. That means that this 20 kilonewton, will cause maximum stress above the neutral axis. Why? Because 20 kilonewton is in this direction and this is tension. Okay? This is the same thing as we did over here. We had a compression and we had a tension. So this tension and this tension, these both added up and we got a bigger tension. So if you are asked to find out the maximum stress at the cross section, you will give this one, not this one. So this moment has got tension above and you have got tension load applied over here. So that means that the above the neutral axis, that is the maximum stress. So you will just plug the values in this one and you will get the maximum stress. Okay, so that's, I mean, it's very straightforward. The only thing in this case is that you have to check where is the maximum stress and where is the minimum stress. That is the important. Okay, why? Because you are interested in the maximum stress which a structure can take. Okay, based on that, in the later classes we will be doing the design.
So it's making a value of 20 and 25.
This is 25, but it is decomposed into 20 and 15. It's 25, but it's inclined, applied inclined. So you have a vertical component 15 and you have got a horizontal component 20.
So the formula, the P is in compounds are used for it.
This P?
Yes.
So this P in the formula is with respect to this cross section. Okay, so in this cross section your P is axial. This is always axial. As we discussed over here, this is the axial load which is applied. So the axial load in this case is 20 kN. Okay, because your moment is made up of is a series of axial loads, isn't it? So moment is series of axial load. Do you agree? This is the moment. This is moment, isn't it? These are series of axial loads. Okay, of varying magnitude. So the axial load will add up always with axial load. You can't just add it up with the shear. As I told you, that load must be in the same direction. So moment, which is actually a series of axial loads plus the applied axial load, which is 20 kN. So we have decomposed the 25 kN into two different loads. Is that okay?
So it's the shear will be effective in property.
No, you can have a shear effect, but the shear is not a combined stress. Shear is not coming in a combined stress format. It's V by A, simple. Because there is no other force which is causing shear. It's only 15 kN. We are trying to find out the combined stress. Okay, the combined is, as I told you, stresses which are derived from loads which are applied in different axes. So that's why. And I mean, similar to this, we have this one. Okay, you have this bracket which is semicircular, and you are asked to find out, for example, load over here at any point, maximum load. So you find out the moments. Okay, again you apply this as a couple. Okay, so but in here you don't know P. So if you don't know P but you know stress, so you can easily work out your P. In this case you knew P, so you found the stress. Okay, this is the same bracket, this is the same type of load, but in this case you don't know P, and you are told that stress must be less than or equal to 80 megapascal. So 80, you will put 80 megapascal in stress. So it's the same thing, only you put 80 over here and you find out your P. The rest of the things you know. Everything would be, this moment will also be in terms of P. Okay? Is that fine? Should I rub it off? The next topic is turn of a section. What is the turn of a section? Turn of a section means, you will see what it means, but actually this is dealing with those cross sections where load is applied off center. Like for example, I have a we have any cross section. This can be a cross section of a stub, a column, or anything. Okay? And imagine our load is applied. So this is the centroid of this cross section, isn't it? If you apply the load over here, then you will have compression or tension. Okay? If I apply my load in this direction, right on the centroid, I would either have a compression or a tension, depending which direction my load is applied. But if I start going off center, okay, like for example, if I apply my load if I apply my load off center, okay, so what happens is that again you will have some moment getting induced. Okay, imagine this distance is E. Now we know that stress is equal to plus minus P by A plus minus N X, because it is in the X direction, and I by Y. So stress is equal to plus minus P by A plus minus M Y X over I by Y. Now, what is My? My is, imagining that this section is B okay, so My is P times, make it EY. My is P times EY. Area is B times H. IYY is BHQ by 12, and X is any direction along this plane. So what I am interested in now is where my neutral axis is going to be. Yesterday discussion, please keep on tossing in your mind, okay? The unsymmetrical bending, I told you that if I change my load, okay, my neutral axis changes. The centroid of the cross section stays the same, but neutral axis changes. So this is the centroid. If I change my load over here, my neutral axis will change. So in other words, as I told you that I will have so I will have neutral axis moving, shifting because of this additionally applied load. I want to find out this neutral axis, what is whereabouts is this. So what can I do? As I told you yesterday, make stress is equal to 0. So if I make my stress equal to 0 is equal to plus minus P by A, which is B A plus minus so this P will cancel out, B will cancel out, H will cancel out. This P will get. So we get, imagine EY into X is equal to H squared by 12. Now X, if I want to maximize my this point, I have to put X as H by 2. So EY times H by 2 is equal to H squared by 12, and that comes out to be EY is equal to H by 6. Okay? So what does that tell you? This is telling me that if I put my load within H by 6, this EY is H by 6, and on this side also if EY is H by 6, if I put my load in that region, I will always get compression. I will always get compression if I put my load within this region. If I go beyond that, I will get tension.
So which point is there?
This is the maximum I have put. The maximum compression is at H by 2, isn't it? So this is maximum. So if I place my load within, so this EY and this EY, both of them should be H by 6. So if I put this load within H by 3, in other words, from the centroid, I will always get compression, and that is called curl of a section. We'll discuss this further in the next class. Okay, so